In everyday life, mass is fixed. 1 kilogram here is 1 kilogram there. But in nuclear world, it's different. A nucleon inside dense nuclear matter doesn't keep its original mass. It changes. It becomes effective. And if we get that effective mass wrong, even slightly, we don't just break an equation. We could be misjudging an entire neutron star. Modeling dense nuclear matter from first principle QCD is basically impossible. That's why we use quantum hadrodynamics or QHD, an effective field theory that replaces quarks with nucleons and gluons with mesons. It captures relativistic effects while remaining solvable. The simplest version is QHD-I, introduced by Walecka in 1974. QHD-I starts from a Lorentz invariant Lagrangian where nucleons exchange a scalar meson for attraction and vector meson for repulsion. The scalar field lowers the nucleon's mass to an effective mass m star, while the vector field pushes back at short range. In mean field approximation, the whole many-body problem boils down to self-consistent equations built around finding m star. By tuning its couplings, QHD-I reproduces nuclear matter saturation around Kf equal 1.30 femtometer to the power minus 1, with a binding energy of minus 15.75 megaelectronvolt or MeV. It predicts a rapid drop in m star over m with density, shaping a stiff equation of state at high density. While it's too stiff for some other neutron star data, its core idea, balancing a huge scalar attraction of about 400 MeV with almost equal vector repulsion of about 350 MeV, still underpins how we think about nuclear forces. QHD-I was just a starting point. Bogota and Bodmer added scalar self-couplings to fix nuclear compressibility. Raw mesons were introduced to handle isospin asymmetry. Later, parameter sets like NO3, PM1, F2 gold, and many others refine the density dependence of the sigma-2 energy and match neutron-rich nuclei data better. But the heartbeat of all these models is still the effective mass mechanism first made explicit in QHD-I. In my experience of modeling it again for my undergrad thesis, I focused on the scalar density integral, the equation that determines m star. I tested it numerically with Gaussian quadrature and compared to the known analytic solution. At first, the results disagreed, and I thought I'd found something big. Turned out I'd written the self-consistent m star equation slightly wrong in my code. The numerical method was fine, but the human using wasn't. Fixing the typo made the result match perfectly. No new physics, just a reminder that a tiny mistake in defining m star can echo through the whole model. In QHD-I, the effective mass m star isn't just another variable, it's a thread that holds the whole picture together. Get it wrong and the binding energy shifts, the EOS bends, and the predicted mass, radius, even gravitational wave of a neutron star fall out of line. A single slip in defining m star can cascade into a completely wrong interpretation of the nuclear world, all the way up to misjudging an entire star. This all gave me some lessons. Even the most established models deserve a second look. I once suspected Walecka's prediction might be off. Turned out the error was mine, and it quietly slipped past unnoticed. That is why we must stay critical of our own result and validate them again and again before making any claim. It is in questioning, not in the certainty, that we keep physics alive. I'm Gita Rahimi, a physics graduate from Indonesia and an incoming Erasmus Mundus International Master on Advanced Methods in Particle Physics student. This work came from late night debugging, a bit of doubt, and a lot of curiosity. Thanks to Walecka, Sarot, and every theorist who leaves just enough ambiguity to keep us learning.